Okay, so let's look at a closely related example here, and we're going to look at a charged conducting shell. So it's supposed to be this gray area. These are pluses here. They are going to be evenly spread out. Okay. I just realized now that I put a big old plus sign in the middle here, which is a little bit confusing. Let's make that into an asterisk. I didn't mean for that to be a charge. I just meant for that to be kind of the center of the sphere. So the gray area, the shaded gray area, is like metal, and we have a net charge on it of plus Q. Okay, and that's spread out evenly. I'll put plus Q spread evenly around the shell. Okay. So this is, this would be like if you had a hollow metal ball and then you gave it some charge by touching it with another charged object, right? You give it some charge. All right. And this is a pretty neat example, okay? So let's again say our goal. Our goal is always going to be to derive E as a function of, I guess, R in this case, like the radius. Okay. We probably should talk about what does that mean in this picture. In this picture, the radius might be small, like it might be smaller than the radius of the charged conductor, or it could be something bigger. And I'll tell you it's going to make a difference because when you're inside the charged shell, you're going to have one situation, and when you're outside of it, you're going to have another one. So we're going to have to kind of distinguish between small r's and big R's. Okay. The other thing I'm going to put in my picture right now before I forget is the radius of the actual shell, which I'm going to give the label big R. And we'll try to reserve uppercase letters for the actual physical dimensions of something. So big R is the radius of the shell. Okay, so let's write Gauss's law. There we go. And this is all about dividing and conquering. Okay, and so we're going to kind of look at cases where you have a Gaussian radius which is smaller than the actual radius. And then we'll look at cases where the Gaussian radius is bigger than the actual radius. And we'll get two different results here. Okay. Now, let's see if you guys figure this out. You see this Gaussian surface here? This is my GS on the inside. That's for R is less than R. That's the dashed circle that's smaller. Okay. My question to you all is, how much charge is enclosed inside of that Gaussian surface, the inner one? Just from looking at the picture. Remember, this is a sphere, right? How much charge is inside of that sphere? 0. Right? Because you're on the inside. Now, what if R gets pretty close to the radius of the real shell, but not quite there? What if it's just on the inside? Does that make a difference? I mean, can you get R, as long as R is little r is less than big R, are you ever going to have anything enclosed? You won't, right? Because it's completely, there's nothing in there. So that's important because if your Q enclosed is equal to 0, then this integral is equal to 0. That implies that the integral is 0. And there's only one way that can happen. There's certainly surface area going on here, so there's definitely, every Gaussian surface is going to have some area to it. So in other words, in order for the integral to be 0, it's the E that has to be 0. And so we get our first kind of interesting result, which is that the electric field inside is equal to 0. Okay? That's how easy it is, right? You're thinking calculus, integrals, scary. No. Because if you pick a Gaussian surface which is spherically symmetric and nested inside the other one, it's not going to give you any field. Guys, we talked about this before from a different point of view. We said, let's say you're right at the middle of that circle. Let's say that you look at a little chunk of charge here, dq. That little chunk of charge is going to give you an electric field that goes this way. That's my dE. Right? It points away from itself. But on a sphere, for every chunk of charge I can find on one side, I can go opposite, and I can find another chunk of charge which will cancel it out. So you see how those two dEs cancel each other out? So by symmetry, at least at the center, all of the dEs are always going to cancel each other out because there's always a chunk of charge on the opposite side of the center. Okay. That's also true for points which are not at the center, and this is kind of the calculus proof. Okay, so I can't make as easy of an argument there, but if I pick a point, say right here, the electric fields also cancel out. It's just a little bit harder to show that. But the integral proves it. Okay, so if we're doing a graph down here of E versus R, I'm going to come down, make this line up with my picture. So I'm going to put my big R there. This is 0. That gives me really 0 for the first part of my graph. Okay. Let's do the second part of this. Let's go outside. So this is outside. I'll write inside up here too. And now again we write the Gauss's law. Okay. And now you look at the Gaussian surface, which is out here. This is R greater than R. Sorry. You're looking at the outer Gaussian surface, right? And I ask you, how much charge? Does it enclose charge? If my balloon is bigger than my actual charged object, I'm including all of it, right? So what I just end up with here is this is just equal to Q plus Q over epsilon. In other words, it includes everything. And then the other side of my integral becomes what it was before. I'll have E dA. Whoops, I'm sorry. So I'll have E dA on the left side is equal to Q over epsilon. And by the usual tricks, that, this whole thing becomes 4 pi r squared. And I get the same answer I got before, which is KQ over r squared. It almost seems trivial, right? But it's the exact same answer we got for the point charge. And physically what it means is that the electric field is picking up where it left off. So the electric field was nothing up until you got to the radius of the shell, and then all of a sudden it will suddenly jump up like a rocket, and then it will start to drop off in the usual way. So it's going to, the function is going to be your typical KQ over r squared, but we just took a bite out of the first part of the graph. Okay? So it's 0 now. And so just remember that it used to be like this. It used to come down like so. Used to do that. But it doesn't anymore because there's no electric field inside there. So your graph is kind of funny looking now. It's got a flat spot, and then it suddenly jumps up and drops off. One of the things that you would have to identify also, like on an AP test I've seen this, is they'll say, well, not only should you make the sketch, but show us what's the value of this point right here. That maximum value. It's not infinity. So if you were to go backwards, the simple way to find that is simply to substitute big R into the equation. And so the value of this would be kq over big R squared. That's kind of this point right here on the axis. It corresponds to that. So when the radius is equal to capital R, the value of the electric field is equal to kq over capital R squared. And then we've fully solved it. Okay. So the effect of having a conductor is to basically wipe out the electric field on the inside. Okay. Because there's no charge that's enclosed inside of that conductor. And the math here is no different than the first example that we did. Okay, you survived.